Thanks for joining me again on the HVAC School podcast. My good buddy, Craig Migliaccio. Did I say that right?
Oh, yeah. That's absolutely right. Thanks, Brian.
Was it actually right that time?
Yes, it was.
I think I always say it wrong, but Neil Comparetto taught me that the way you have to say Italian last names is you do this, and then it makes it all right.
That's right. Yeah, that's right. That's
yeah.
right.
Yeah, I hope that's not like going to get me banned or canceled or anything. It probably will happen. Actually, worse than that, when you make fun of Italians, they just kill you. So that's that's all.
Don't worry, we'll handle this later. The family will handle it.
We'll just it'll be fine. It's no problem. Anyway, so today we're going to be talking about mini splits. So apparently you've been working on a book. So let's get that out there, out front and center first off. How's that going and what's that all about?
Yeah, so inverter mini-split operation and service procedures. We've been working on that for 2 years, and we have over 400 custom images in there, and we were painstakingly going over all of the words in there. So we have 326 pages, and the whole point is to try to demystify how an inverter mini-split works, why they're becoming more and more popular, and basically allowing technicians to feel more comfortable in troubleshooting because you can divide the system out into individual parts. And if you know how the individual parts work, so then you're going to know how to troubleshoot them better and feel more comfortable. So we have the refrigerant side, then we have the electrical side. And so we got the book split up into 2 sections. And so I just think that's how you have to do it. You have to split it down to the very small level, and then you can add up all of the details later.
That's one of the things that you're always really good at, is breaking things down to their constituent parts. So many of your videos, you'll have the parts all kind of laying out in front of you and talk through them in a really sequential way. And so I think it's great that you're tackling this, because it's one of the things that we get so many requests from people about. I'm sure you get it all the time. It's like, I need to know more about how to troubleshoot and install ductless systems or mini splits. So let's start with the basics here, because again, this obviously we're going to talk a little bit about the book, but then and kind of what's in it, but also just introduce some of these topics, and at the end we'll talk more about when to expect it out and all that. But mini splits in general. So what makes a mini split, and how do you kind of think about that? What makes them unique, I guess?
So they're compartmentalized. You have a side air discharge outdoor unit. You might talk about them in that manner. The electrical cabinet is separated over to the side. You don't have like with a central heating and air conditioning system, a central ducted system. You have the rainwater coming right into the compressor area where the accumulator is. All this stuff is shielded. A lot of people think of mini splits as the ductless units, and that's how they originated. But now you have ducted units, and so you're always going to be playing around with what to call them. So you have many different types of indoor units connected to an outdoor unit, or you could have a multi-zone outdoor unit connected with a bunch of different indoor units. So a mini split covers a lot of different indoor types. And so a lot of these are all inverter driven. And so it's higher electrical efficiency and more of a capability to draw heat out of the low temperature air outside in order to heat the building during the wintertime.
Yeah, it took me so long before I really understood how that worked. Like when I heard things like hyperheat, or when so like these heat pumps that can work down to a much lower temperature. It took me a long time to get that. Like, yeah, how they do it is that they spin the compressor faster. Like, it never caught on. But you'd hear it. Like when I first started working on a green speed unit or whatever, and they would it would be low temperature outside. You'd hear it'd be kind of loud. And really, that's, at least to my understanding, that's the big difference. Now, obviously, all the controls that support that, and a lot of times you have to have some form of interstage cooling and some method of vapor injection of the compressor, something that kind of keeps the compressor from overheating. That's where the secret sauce is. But really, at least to my understanding, that's a big part of how these inverter-driven compressors get that additional heat out of that outdoor air.
Yeah, so a lot of the hyperheat systems are, if you're talking about, say, like a 12,000 BTU unit, it may actually be a 15,000 BTU unit that is limited down due to its programming. And so they have the EEPROM chip and they're programmed by the factory. So basically it's going to be limited down to a lower capacity for the compressor until the outdoor temperature gets down gets down low, say 32 degrees or 20 degrees, and then it's going to allow it to run at, say, 100% or 110% of its actual capacity. So then you're running at 15,000 BTUs, even though it's technically rated at 12,000. And so it's pretty cool when you look at the performance charts, and you can look at the COP, so that your coefficient of performance, and the actual BTU output of, say, a hyperheat system at negative 11 or negative 22 degrees, and you kind of walk it through up to, say, 50 degrees, and you can see how much output you really have. So maybe on a negative 22 degree day, like say a 22 SEER unit, you might have half of the BTUs than it's rated for. So if it's 12,000, the system size may actually be 15,000, but you wouldn't know that. And then it might produce, say, 6,000 when you get down to that low of a temperature. But basically, it all comes down to the sizing for your building and what you really need for the building.
Yeah, it's the way I kind of like to think about it, and this may be a stupid way, but I'm kind of a stupid person, so it makes sense to me at least. When you have an ECM motor, when we replace PSC with ECM, it's kind of similar to what happens when we replace inverter-driven or regular, I guess it's again a PSC compressor with a inverter-driven compressor. In terms of the programming, because what happened was, and I recently just did a podcast on this with Chris Mahali, where we talked a lot about ECM motors, which I know I'm saying motor when I say that. Okay, so just waiting for the trolls to correct me on that. But when we went to these ECM motors, now we had programming where we could maintain our airflow, at least to a certain degree. So you could have the same airflow at 0.1 static that you had at 0.6 static, say, as an example. But that doesn't happen for free. That motor has to actually spin up in order to maintain it. And so now with inverter-driven equipment, that traditionally you would have seen this massive drop-off in capacity as those temperatures get lower. Now they can help maintain that capacity because, like you said, you have a little bit of oversizing, but you basically have the ability to bump up that capacity in order to compensate for it because you're still fighting against those same forces. In the case of a compressor, you're fighting against higher compression ratio because as that outdoor temperature drops, your evaporator, which is your outdoor coil in this case, is now in much lower conditions. And so in order to get heat out, that temperature's got to be lower, and so your compression ratio is much higher. So they just have that kind of intelligence that allow that to happen, which gives you that capability of low ambient heating, which is super important for heat pumps because obviously in the past, that's why in northern climates, a lot of people couldn't use them and wouldn't use them is because they just couldn't perform on the coldest days.
Yeah, and so at the 0 degree mark, 0 degree outdoor ambient temperature. So for, say, a 12,000, I'm just using a 12,000 BTU single zone system, but if that's a hyperheat system, you might actually get 12,000 BTUs of heat output when it's 0 degrees outside. If it's a non-hyperheat, you might get maybe 12,000 BTUs of heat, maybe at 20 degrees outside. And so the hyperheat system may allow you to operate at a decent rating down to a lower temperature. But yeah, it's really cool because the system takes many different temperature measurements with the thermistors, and it makes decisions for operation based on these pre-programmed algorithms. What's not cool is we can't see them, and that's what's frustrating. And a lot of technicians go around there and they want to go to a training class, and they're saying, "Tell me that secret sauce. Tell me the secrets." No. You're telling me the sales things. Tell me more details.
Yeah.
And so that's that is going to be the frustrating thing, is because a lot of times you can't see it.
Yeah, and that's one of the distinctions between mini-splits and VRF VRV is that usually in the VRF VRV world, the engineer, the service technician, has a lot more ability to adjust the parameters. Not only can you see what's going on a lot more, but you have the ability to adjust it. Whereas a mini-split, which is generally designed for more light commercial residential applications, is a little bit more locked down. It's sort of like your Apple phone, where your iPhone, where it's like you can't do as much with it. Whereas if you have like a Linux computer or something like that, where you can program everything, but it's not as user friendly. So that's kind of the balance that they're always playing, and it's understandable because a lot of people who are going to install mini splits or ductless systems are going to be not quite as experienced as the people who are going to be doing VRF VRV. But another thing that distinguishes them, and I wonder if you could talk about this a little bit, is the location of the metering device. Because in VRF, VRV, the metering devices tend to be in branch boxes or sometimes even at the heads, but it's different with mini-splits.
Yeah, so a lot of times, so in this book, we draw a comparison between, say, a single zone system and a mini-split inverter system. So any mini-split is going to have the metering device in the outdoor unit. So, and what's funny is actually some mini-splits, you can technically get away with calling it an inverter, even if you have, say, a capillary tube as a metering device. You're either going to have capillary tube or an EEV, and the term inverter is really talking about the compressor drive. And so, but the high efficiency inverter systems are going to have your inverter-driven compressor. You're going to have an EEV, electric expansion valve metering device, in the outdoor unit, and then you'll have a fan motor in the outdoor unit as well. It's most likely inverter-driven, and at the indoor unit, you're going to have a either speed control board inside the fan motor or outside the fan motor, and some of those are also inverter-driven as well. But the metering device itself, where you're talking about is kind of a question why we don't have filter dryers in a inverter mini split. And the problem is you don't have subcooled liquid in the same spot at all times, regardless of whether you're going in air conditioning mode or in heating mode. And so that's like a major reason why we don't have that, as well as a lot of them having PVE oil, which doesn't necessarily develop into acid when you have water getting trapped in there, but it doesn't allow for as good of a lubrication if you have water mixed with the PVE. But yeah, so the metering device is always in the outdoor unit, and something that was pretty cool, we were forced to have to learn all the little intricacies of the EEV and how it works. And, when we come down to the HVAC symposium, HVACR symposium down there in Florida at your place, we're going to start discussing those things. And so thanks for having us down there for that. So that'll be exciting.
Oh, you now you ruined it. I was going to save that for the end, and now everybody already knows the main secret, which is they're going to be down there. So when we're talking about, there's a couple distinctions. When we're used to working with unitary equipment, we're usually working with POE oil. And our metering devices are usually right in front of the evaporator coil, which means that we have this liquid line that just changes directions. And so we can put a liquid line filter dryer in that liquid line because it's always liquid and it's just changing back and forth. Well, with these ductless systems or mini splits, and again, not VRF, VRV, they're different. And again, because they typically have traditional liquid lines. But with mini splits, the metering devices are in the outside unit. And that's one of the ways that's one of the distinctions that I would make. If it doesn't have the metering device in the outside unit, but it's side discharge and has heads that look like ductless heads, then I would call that a VRV or VRF system, even if it's single phase. But that distinction of having it in the outside unit means that you don't really have access to, at least in cooling mode, you don't have access to a high pressure line. So at least not outside of the equipment. And then, to your point, that's also why putting a line dryer in doesn't make sense, because then any pressure drop creates a real problem. You don't have, a pressure drop would be a major issue with the operation. And then that leads to the reason why we don't braze on the lines as well. And the reason why it's so important that we handle them really carefully in terms of getting contaminants in it, because you don't have that filter dryer.
Yeah, absolutely. And same thing, say, in heating mode, when you just have a vapor port and somebody wants to check the total superheat, you have your discharge gas right there, going to your indoor unit. And so you can use, say, total superheat, you can measure it, in air conditioning mode, and that may help you with troubleshooting, but you can't necessarily check the refrigerant charge with it unless the manufacturer gives you some type of guide and some way to, say, lock the system at certain operating parameters. And that's a frustrating thing for a lot of the technicians. But going back to your point, once again, in reference to the EEV in the outdoor unit, both lines are going to be low in temperature during air conditioning mode. And so they both have to be insulated, and we make sure to seal the ends of the insulation. We're trying to avoid any type of moisture getting up in there and air getting up in there, and any type of corrosion happening with the insulation and the lines as well. You want to have both the liquid and the vapor lines insulated outside and through the building to make sure that they don't sweat, and they're both going to sweat during air conditioning mode, so that's a big deal.
Another big thing with ductless systems in terms of installation is the flaring piece. And we have kind of a funny history with that. I don't know if you remember when we were trying to make flares in the office, and I was really bungling it. But anyway, that's neither here nor there. You're not going to bring that up. You don't want to. You don't want to embarrass me. So, what are some of your kind of like top tips as far as that goes? Because we've already mentioned. It's got PVE oil in it, which means that you don't want to get moisture in it, but at least it's not quite as hygroscopic in terms of it's not going to change. Well, it's very hygroscopic, but it doesn't change into an acid, so it doesn't have that hydrolysis that POE has, which is a good thing. But we still need to make sure, obviously, that we don't have leaks. Again, they don't want us brazing in most cases because they don't want the cupric oxide getting inside the tubing. But what are some of your like best practices as far as doing the flaring part?
I really like eccentric flaring tools, ones that have an offset cone so that when it's drawing out the flare, it's not pressing on the entire tube the whole time, so it produces less friction. It's easier to turn, especially if you have a manual one. You know, there's plenty of battery-operated electrical ones and ones that you can attach a drill to do your flaring process faster, and that's absolutely fantastic. And they have a depth guide, and so you can just set them right in there and keep making flare after flare after flare after flare. It's a lot different than when, say, I came into the trade and just using a standard flaring block. I love using any type of form of eccentric flaring tools because it doesn't scratch the flare when it's all done. And I like to make the flare face a little bit bigger than maybe some of the stops are on the flare blocks. But anyway, getting to the point is that I use a round reaming tool to deburr, or a round deburring tool to deburr the inside edge of the copper tube after cutting it, because you have that sharp edge. And then I like to have like a little refrigerant oil on the eccentric cone in reference to making the flare, basically drawing it out. Obviously, or maybe not obviously, putting the flare knot on ahead of time. It's a big deal. Yeah, nothing more frustrating than that.
Yeah. I've confessed, I've done it 3 times in a row where I've made it and like, shoot, I forgot to put the flare on it, and made it again. Shoot, I forgot to put it. I've literally, that's how bad I am. So yeah. Do as I say, not as I do in this case.
Well, that also comes to doing a lot of different things. Your mind is in like 20 different places, trying to set up multiple jobs and things, and sometimes that kind of stuff just happens, unfortunately. But yeah, so you put the flare knot on, you make your flare, and what you want to do is you want to slide your flare knot back over the finished flare when you're done, when you release it from your block or from your tool. And you want to make sure that the flare that's drawn out basically is taking up the majority of the inside of the flare nut. And speaking of the flare nut, by the way, you want to make sure to use the manufacturer's flare nut, not necessarily just the flare nut that came with the line set, because it might be too small. It might be like a plumbing flare, instead of something that's rated for high pressure and from the manufacturer and is rated for the torque values that you're going to tighten it down to. But anyway, you slide your nut over the flare, and then, so that's good. Then you slide your nut back again. You can kind of just eye up where the flare goes and connects over to the flare face and the flare adapter. Make sure it's covering the entire surface. That's a big deal. A lot of flares that I see, especially ones that are pre-made, are only like halfway made, halfway done. And this with a bad flare nut. So you end up cutting it off and just making your flare anyway. So you make sure that's all seated right. Make sure it's a 45-degree flare. You fit it to the flare face. Everything looks good. You then go ahead and hand tighten your flare nut onto the flare face. It's usually on a two-way or three-way service valve. But you have that. You're tightening it down, and then you're going to hold your service valve with a wrench, a whole back wrench, maybe an adjustable wrench, but you just want to make sure you're holding that. And you're going to use a torque wrench, and you're going to tighten the flare nut down to the specified torque value for the copper tube diameter size. And some manufacturers recommend 2 tightening torques, a lot of them are just 1 tightening torque. If they recommend 2 tightening torques, you tighten it to the first torque, then you loosen it. You tighten you adjust your torque wrench to a higher setting. It's usually like, I don't know, around, say, 5% higher, and then you adjust it, and then you're tightening it a second time. You want to make sure to follow the manufacturer specifications for their specific flare nut. And another thing I see a lot of people doing is putting lubricant on the threads of the flare face. That messes up the torque value. A lot of them are dry flare face, but once again, you read the manufacturer's literature in reference to doing that. Also, a lot of people, including myself, have done, and you can put a gasketing material such as refrigerant oil or nylon on the flare face before you tighten it in. I've also done experiments where it's just dry, just copper against brass, tightening it to the proper torque specifications, putting it up to 600 PSI, letting it sit, and seeing how much I can get the leak out over like a 1 month period. And pretty good. I didn't really see any drops. And I had like, I don't know, 12, well, maybe about 30 flare joints, just testing it, playing around with it. And I did a video on that, but I was kind of curious myself. I don't know. I know everybody does them differently. I don't know what your perspective is on that.
Everything you said is wrong. No, I'm just kidding. No, those are all the high points. Yeah, I mean, there's a few little like we're a little bit more heavy with the nylog in general, but to your point, if you follow the ways the manufacturer tells you to do it, you're going to be safe. And the biggest thing are these sort of just obvious best practices, like making sure you don't have scuffs on the flare face, making sure the flare is the right size, making sure that you're kind of mating it up against and just does it line up? Is everything the way it's supposed to be? Using the manufacturer's flare nut. That's actually a really big one that I often forget to mention. So thank you for mentioning that. And then pressurizing it up to that high test pressure and letting it sit, putting some still soap bubbles on it and making sure you're not getting any microfoam. Those are your best practices. If you follow those, you should be just fine. It's something always worth mentioning, though, because in terms of challenges that people face with ductless systems, the flares are often really high on the list.
Yeah. Absolutely. And to your point with pressure testing, I always recommend digital gauges, either probes, wireless probes, or just digital in general, because it's very important. You'll see the pressure drop real quickly instead of a compound gauge where you have to wait a longer period of time. Likewise, though, with a used system, you don't want to pressurize it too high because you could make a leak. It's kind of that old situation we had with the old R22 coils. When you're pressure testing it, you can make a leak instead. So the digital pressure readout is going to give you a quick turnaround time as far as if you have a leak or not, and using non-corrosive bubble leak detector on the joints. Anytime I pressure test, I always put the non-corrosive bubble leak detector on those joints to see if I see any glistening whatsoever, and absolutely, that's what you want to do.
I like the term glistening. That's a new one. I haven't heard that one before, but I like it. Another thing that a lot of people mistake when they think about pressure testing on these is they'll say, well, high-low pressure, how does that work? Low side pressure versus high side pressure. Well, keep in mind that in this case on a heat pump, your evaporator coil is on the high side because in heat mode, it's going to be on the high side. Both of those lines are going to be on the high side in heat mode. So because of that, you can pressurize the evaporator coil on the line set to that higher pressure. Just keep in mind your only risk there is pushing back through the valves. The weakest point in the system, and this is almost universally true, is the actual fusite or the terminals, the kind of glass terminals on the compressor. And this is something that I didn't know for the longest time, is that the actual body of the compressor is on the low side because your suction gas dumps into the shell of the compressor and then is pumped out. So only the head of the compressor is on the high side. So really what you got to be careful with when you're pressurizing on any system is pressurizing the shell of the compressor to that higher pressure. That's where you can generally do the most damage. But to your point, on an older piece of equipment where you may already have some corrosion going on in the evaporator coil, maybe you already have some tiny leaks, that's where pressurizing it to that higher pressure, you can, if that's the old saying, like if you didn't have a leak, you just made a leak by using such high pressure. So,
yeah, that's the shame of it. And yeah, you need to be careful. And the same thing with diagnosis of the compressor, you do it at the wires connecting to the compressor before removing the plastic cap. If you get your good readings there, then you know that your connections are intact. But if you're going and pulling on those terminals, once again, like you said, that's the weak point, and you better darn be wearing safety glasses in case that was to pop off and have refrigerant come at you. You got to be careful with those types of things. So you start with the wires connecting to the compressor with your diagnosis, with the system off, checking your resistance values, and then you kind of move closer to the compressor as you need to. Because if you have an improper reading at the wires, it could be that maybe a connection has melted or was loose or something like that at the compressor terminals themselves.
And this is what I love about you, is that you're so rigorous in terms of your processes. Like, I'm all over the place. Even today, if I were to diagnose a system, I'd be like, "Oh, check this and check that and try this and try this." Like, you're very, very rigorous and thoughtful in how you describe those things, and it's a really good point. All very true. So, okay, when you're thinking about like the parts and service of the equipment, what are some other things We've talked a little bit about some installation things. Obviously, it's worth mentioning before we move on here. You pull a vacuum like you would in any other system. Weighing in the charge properly is massive with ductless systems. Also in VRF and VRV, same thing. Especially when you have multiple heads and all that. You have to pay attention to what the manufacturer tells you in that. You got to get that dialed in exactly right. But what are some other things that we need to think about in terms of operation, parts, and service?
So let's start with the main causes for failure, and a lot of them, like you just hit on, was refrigerant leaks. Is you come up to the system and it's either flashing an error code or it's just running at very low pressures. That's one of the big things. Number two, and of course you're gonna have to a lot of times it's at your flare joints or the corrosion due to that insulation on the tubing or something like that. You could also have evaporator coil or whatever, or indoor coil leaks. But in reference to the other things, you could also have voltage spikes or lightning or something that has damaged the main PCB in the outdoor unit or the IPM, the intelligent power module. And so you want to have a surge protector on the outdoor unit, and you could also potentially install some type of a voltage monitoring system with surge protection to temporarily short that to the ground if you have a lightning strike. That's a big thing, is with these circuit boards are very sensitive. But another thing is the thermistors, and a lot of times people ignore those and they get out of calibration. You have a tube thermistor or a bead thermistor, and that's something that with the system powered down, you can check the electrical resistance values of that and compare that to the temperature. So a lot of times I'll take a temperature meter, I'll tape that temperature sensor to the bead or the tube to make sure that they're at the same temperature, and I'll use the manufacturer's chart while measuring electrical resistance and making sure it's very close. Because if you're, I forget what it is, it's like maybe 7% off, you're talking like 3 to 5 degrees off, and the whole system's parameters is based on that. And so you're totally jacked up at that point, with your efficiency. So that's a huge deal, and you have multiple thermistors to check.
It's a really good point, because everything is so algorithmic. Everything is based on these interdependencies of boards and temperatures and thermistors. They can drift. It's something that can happen. And kind of to your point, that's how you test them, is you just power it down, disconnect, take your own meter, connect it in, reference the chart, and see if you're actually matching what it's supposed to be.
Yeah. Yeah. So, another big thing is when you're doing preventative maintenance, you mentioned, as far as the dust on the back, people think, oh, it's just my efficiency that's lowering a little bit. I'll get to it when I get to it. Well, it's a big thing. And in fact, the intelligent power module usually has a aluminum coil, a heatsink coil that is in the airstream of the outdoor unit. So that outdoor fan is pulling air not only across the coil, but across the IPM, not the whole module, but just the heatsink. And the IPM, because it's doing that conversion for the electricity to change basically single phase electricity into 3 imitated phases of DC power to power the compressor. We can get into that in a little bit, but it needs to lower in temperature because it's going to have a lot of heat on it. And so if you have dust on that upper part of the coil, you're not going to have that good airflow across the IPM, and it could overheat and fail.
Yeah, really good point. Also, another thing to mention, just while we're on the subject of that particular feature, in some cases, you're going to be replacing circuit boards, and you have to actually mount them to an existing or a heatsink that stays in place. If they send you that little tube of paste, you need to actually use it. That's actually important. Talk about that just a little bit.
Yeah, the thermal conductivity of it, you definitely need to pay attention to that and apply that so you have proper heat transfer. If you do not, you'll have a separation, and that's all you need is a tiny little air gap in there. Air is insulation. And so it will not work properly. It'll be a kind of a fake thing, and then you'll be replacing the circuit board again. And some IPMs, they have refrigerant tube heat exchangers, so it'll just be maybe a U tube of copper of the vapor line heading before it goes to the accumulator on the side of the compressor. It'll cross the IPM, or it may even have its own zone that is to lower the temperature, on that heat sink. So that I just refer to that as a block, like a tube block on the IPM, and so it could have either one of those in order to lower the temperature. So just be aware of that. Now, I believe manufacturers are moving to that. because of the poor maintenance that's being done on these systems. So it's kind of like one of these things where maybe the manufacturer gets blamed. Hey, your electrical components keep failing, and it's a preventative maintenance issue. And so that's a kind of a big point for cleaning these things. It's not only efficiency, it's the lifespan of the unit.
Another thing I'm going to mention, and you don't necessarily have to agree with this one because this is probably kind of controversial. So I'm just saying that off the top. But in our market where it's very hot a lot, if anybody who's been to Florida, you kind of know, and this is true of other markets too. It does seem that you have more circuit board failures, more issues when the system is in direct sunlight. And so even just thinking about the location, if you can kind of decide where it's going to be. Now, don't do something dumb like put something over it that's then going to restrict the airflow or something. You know, like that's not what I'm saying. But if you have a choice of where to locate, and this is really true not only of ductless but also of unitary equipment, if you can locate it in the shade or if you can locate it on the north side of the building, then do that because it does matter. I mean, like it does it matter massively? Well, I mean, maybe not, but especially when you have circuit boards that are heat sensitive. I've just noticed in what I would say is not insignificant amounts that we seem to have higher failures on systems that are in direct sunlight, especially on those exposures that tend to be the worst, which the south, of course, is generally the worst.
Well, I wouldn't say that's controversial at all as far as my perspective. I think that's right on the base. You know, like that's absolutely what you want to do. And when you talk about, say, single speed systems, you have a capacitor in there. If you're replacing the capacitor every year, well, guess what? There's a problem, you know, and it's most likely that capacitor is overheating because the electrical cabinet is just sitting in the sun. And so it's failing because of that. And so well, guess what? You have capacitors on circuit boards. And so if that cabinet, the electrical cabinet, is just overheating, that sun is a lot of heat energy. I mean, that's what heats the earth. You know, like
last time I checked, yeah.
I think
so, yeah.
So that's a big deal. Yeah, if you could locate these systems where they're going to stay in the shade, that's a huge deal. No matter what system you have. And the same thing for efficiency too. If you're trying to reject heat and you have the sun beating on the coils and everything, I mean, that makes sense. So definitely that. And then the other thing is with a Mini-Spli outdoor unit, the other big thing is don't try to spin it away from the house and do it kind of long ways. I've seen some weird stuff before where they're in just different orientations where now you have the sun beating on the exposed temperature sensor, which is the thermistor, outside, and you're totally throwing things off. Then it's no good at all.
Yeah, they're really designed to have that coil up against the building because that does it that shades it naturally and also keeps that temperature sensor in the shade, which is huge. I mean, any sort of thermistor, any sort of temperature sensor at all, whether it's a thermistor or a thermocouple, if it's in direct sunlight, it's not going to measure correctly. And so that's a huge factor and something that honestly I don't know that I've ever thought about, at least not in that way. So you know, I always learn when I do podcasts with you. So
you're always trying to elevate the person that you're like trying to talk them up and everything.
I'm just telling the truth. That's all I'm doing. I'm a man who speaks the truth. Okay, all right. That's all it is.
You use all your fancy words, and I just nod, and I'm like, "You're right. You're right. You're right." I don't know what you're saying, but you're right. No, so even things like when technicians are checking the charge, that's a big deal. You have your temperature clamp or your bead temperature sensor in that case, and you're trying to check the refrigerant charge or something like on single speed systems. You have the sun beating on it. Well, guess what? You know, your temperature is not correct. You want to put some insulation on that or make sure that you're in the shade. Even putting a glove on it or something like that to cover it while you're doing this is a big deal. So, yeah.
Talk a little bit about charging, because not only initially, because we talked about that a little bit, but if you go to a system and now there was a flare leak, I mean, I know that's never going to happen, but as in it happens all the time with ductless systems, or you have one of these line sets that fails on you or whatever, and now you have to recharge the system. What's some best practices there?
So if you suspect a refrigerant leak, I would suggest just searching for it at the flares real quick with non-corrosive bubble leak detector. What does that cost you? How much time? Not a whole lot. The indoor unit, that's kind of a different thing. You're trying to lift the unit off the wall a little bit and you're trying to cut the insulation back. That's a kind of a big deal. But if you could at least start at the outdoor unit, just at the flare connections, that's one thing. with the system off, if it's been off for say 10, 20 minutes, the refrigerants most likely have equalized, but you also don't know in the equipment manufacturer's programming if the EEV is shut in the closed position or if it's open. You just don't know. But basically it should be able to equalize, and you can check the pressure at the outdoor unit. So you can say it's 80 degrees outside and 74 degrees inside. If you measure the pressure and you convert that to a saturated temperature for the refrigerant that you believe to be in the system, like it's a fairly new system, it has R4 10A or something like that. Obviously, we're going to be switching over to R32 here soon, but R4 10A, it's in there, and you are measuring a saturated temperature of like 30 degrees. Well, then you've leaked out 7/8 of your entire refrigerant charge because your refrigerant's no longer saturated. And so that's a key indicator, but that will not tell you if you're just a little bit low. That's like a massive amount low. That means that there only is vapor left. When I say you need to take your pressure and convert it to saturated temperature of what you believe to be in the system, you need to look at the rating plate. You could even look at the compressor on the side. You need to verify that you're not talking about an old R22 system. Most of the inverter systems are R4 tonight here in North America. A lot of them have been R32 for 2 decades, overseas. So, that's one thing that you can do. Another thing is if you see that the line is severely frosted or iced over, it's most likely undercharged, or it could be other things as well. Like a thermistor is telling the system that it's reading an incorrect temperature, or you could even have the EEV maybe has rust between the head and the stainless steel shell, and the magnetic field is not really getting to the inner permanent magnet within the EEV, and it's not able to open up more. So it could be multiple things. You can't just blame it on the refrigerant charge. Now, while it's running, if you measure maybe a total superheat of 30 degrees or 40 degrees, well, then, once again, you think it's low on refrigerant, but it could be some of these other electrical devices. So that's what you can do. Now, if the system is running with, say, a total superheat of, say, 20 degrees or lower, then that's more along the lines of the range in which it's going to be operating. It's normally, a lot of times, these systems are running with a very low total superheat, because the entire coil is a lot of times is filled with saturated refrigerant to absorb a larger amount of heat. So talking air conditioning mode. You're from Florida. You understand this.
Yes, I am. Last time I checked, I went outside. It was Florida. Yeah, so we're good.
It's cold here, and you're like sweating when you go outside down there.
It is. It's raining, so I would be wet and not from sweat. But that's it's hurricane country. So
yeah. So you don't know the programming, right? So you don't know what's happening. You also don't know if the user has set the indoor airspeed at a certain amount. So the system, even though it wants to control that, it may be locked at a certain amount. You may want the airspeed at the indoor unit at a low amount. Well, then the system can increase that airspeed just a little bit. It's not allowed to, increase it to medium speed or high speed at that point. And so you've limited the system. So when you're trying to quote unquote check the charge, there's a lot of factors that are going to change what your refrigerant charge level is. You don't know the speed or the capacity of the compressor. You don't know the speed of the outdoor fan, the indoor fan. Is it set on auto or is it set on medium? Do you have it all the way up on high speed, your indoor fan? Because then you're going to have a higher heat load at that indoor coil. These systems measure these thermistors maybe every 20 seconds, 30 seconds, maybe every 2 minutes, and it's making operational decisions and changes that you don't know. And so the manufacturer would have to give you some way to lock the system at a certain amount and have to give you like a target superheat guide that it should be ranging at. But the big secret here is that these systems don't work on necessarily subcooling and superheat. They work on the temperature. Well, let me rephrase that. They're not trying to. Don't laugh at me.
I was laughing with you. You were laughing first, and I laughed. So
it's weird. A lot of people are laughing with me. That's so weird.
Yeah. Superheat and subcooling does not exist in these systems. They work on electromagnetic fields. Anyway, sorry. Go ahead.
Yeah. No. So they're measuring temperatures, right? And they have programmed algorithms to work on monitoring all of these temperatures from these thermistors. And some systems, they'll have pressure transducers, but the majority of them are going to have thermistors because they're lower cost and they're simple. And so when all these things and the parameters are functioning properly, you're going to be at an efficient superheat and subcooling. That's the bottom line. And so it's not measuring superheat and subcooling to adjust the system. A lot of times it's measuring temperatures to maintain a efficient superheat and subcooling. So what you may measure if you run the indoor fan at medium airflow speed, and you set the temperature down low and you give it, say, 10 minutes and you're like, hey, it's adjusting to hopefully what it wants to be at, but once again, it's constantly adjusting. You may measure a total superheat outside of 0 to 10 degrees or even 0 to 5 degrees. It may be 1 degree. And it's allowed to run at 0 degrees of total superheat because it has that accumulator on the side of the compressor that's going to be a protection device for the compressor to make sure that you don't have liquid or saturated refrigerant entering into that vapor compressor. And so it's able to do its job in a real efficient manner.
Yeah, so to start with, I guess to kind of summarize, it's hard to check the charge in the traditional ways we would be used to. It's not that it's completely useless, but it's not the same. It's not like you hit a target, superheat or subcooling. But the first thing to do, I would say, would be just make sure everything's clean. Like, especially if it's not if it's not a new system, make sure the condenser coil is clean. Make sure the blower wheel is completely clean. Those things get gummed up a lot on mini splits. Make sure the evaporator coil is clean. Make sure the airflow is how it's supposed to be. Doesn't have bushes growing into it or whatever. Make sure that you have proper clearance up above. Make sure your filter's washed. All those things, so that way your airflow is going to be properly set. And then if all of that is good and you're still not getting the performance out of it that you would expect, maybe it's continuing to freeze or whatever, well, then at that point, I would probably weigh the charge out and just see, are we low or not? I mean, would you agree with that?
Absolutely. Yeah, that's the thing, because when you recover the refrigerant charge out of the system, you turn the system off and you recover all the refrigerant. You're going to see if the system is low compared to the factory charge that's listed on the outdoor unit rating plate. And then you also have to, in some cases, it's a guesstimate of the line set length and the path, so you're trying to go, okay, a lot of times you can't see it's in the walls. And so you see where the indoor unit is, and you're measuring the floor length and then the heights. And when there's multi-zones, you're adding it all together to come up with a cumulative line set length. And then you're taking that and looking in the manufacturer's literature or the rating plate. Sometimes it's not on the rating plate where it says, if it's R410A, it might be, say, 0.16 ounces for every foot, whereas some other manufacturers might say it's 0.24 ounces for every 1 foot of, say, a 1/4-inch liquid line. And so that's the other crazy thing about it, is half the manufacturers have the low amount of liquid refrigerant weight per foot, and the other half have a high amount. And it's just based on their accumulator fill rate when they're designing their systems. And so the technician really needs to pay attention on what manufacturer they're working on. So anyway, with that being said, you recover the amount of refrigerant, you look at the factory charge. You also have to look at how much line set that is supposed to cover. It may cover up to, say, 35 foot, and then anything after that, you have to add. So if the factory charge says it has 3 pounds of refrigerant, you have to then add, if it's another 6 ounces due to the additional line set length, or maybe 4 ounces or whatever, then you compare that to what you just recovered out of the system. If you recovered only 2 pounds of refrigerant or 1 pound, you're severely low. You know the answer right away. You don't have to guess. And that's the problem, is if you recover the refrigerant and you know it immediately, you have a leak, you already know the problem. And that's the majority of the problems with these systems, is due to some poor installation procedure, especially if it happens a year after it was installed. You kind of have a general idea it's probably the refrigerant charge. So you make a great point, and that's that you need to recover the refrigerant to weigh it to see if you have a refrigerant leak, and every other test that you're going to do is going to point to more than one possible cause. So you're not going to know.
Yeah, and then from there, it gets real tricky if you didn't have a refrigerant leak and you thought that you did, and now you've got to go through all the other components and all of that. But in most cases, you're going to find that you do. To your point, as soon as you suspect you might have a refrigerant leak, before you even pull the refrigerant out, go ahead and soap up the flares that you can get to easily. And then even if after you pull it out, if like, okay, now I know I'm low, well, then you can use your favorite leak detector and even go back in with nitrogen, and maybe not full pressure if it's an older system, but maybe you go back in 300 PSI, something like that. And now you can use that ultrasonic leak detector to further locate the leak.
So definitely, yeah, you can use the ultrasonic leak detector because you have oil inside the tubing. It's going to make that squealing noise. That's a nice tool. There's a lot of tools that you can use, so you just want to make sure that it's one that's for that correct refrigerant. Some different refrigerant leak detectors are made for specific types. If it's a HCFC versus a HFC, it just depends on what kind. Anyway, so definitely, if you don't find a leak when you recover the refrigerant charge, then you're going to have to do that whole process. You're going to have to vacuum it. You're going to have to then weigh your whole refrigerant charge back in again, and you're going to typically do that out of your new refrigerant bottle, not your old recovery bottle, because you might have multiple charges on there, and you're not allowed to basically take somebody's refrigerant from one owner's site and put it into another owner's site, and plus you have dirty oil in there possibly. You don't want to put any air contaminants. You want to make sure that you are doing everything that's right. So after you do that whole procedure, then you still have to do the whole checking the electrical resistance values of the thermistors, checking. You can see the EEV head to see if there's rust on it. That's a big one. But a lot of times those are insulated, and so you have to peel off the insulation in order just to see the EEV head. You want to make sure to not nick the wires. Sometimes even with the thermistors, it's not the thermistor itself. It's the wires have got chafed, and that's a problem. But during this whole time, the big thing is you have to notify or continue to speak with the building manager to let them know, because it can be a decent amount of work, and you have to let them make their decisions on, can I go to this next step? Are you willing to pay for this next step? Because you can get into a problem where you spend too long on a job and maybe potentially can't fix it. Maybe you need to stop at a certain point, or maybe you need to call tech support, or maybe you don't have the manufacturer's literature. You got to find it, or you can look it up with the online app. And so you definitely want to keep the homeowner, informed of your process through the whole thing.
Yeah, for sure. Because it can be really simple, or it can take a while, especially when you deal with certain electrical problems that you're kind of chasing. Sometimes it can take a little bit to go through with tech support and work through, checking everything. You got to make sure you're not condemning incorrect parts. All right, we're already at 45 minutes. There's so much more that we could cover on this, but rather than covering all the rest of this on a podcast, I think we'll just have people buy your book. So when is it coming out? Where can they get it? Where can they find out more about that?
So at our website over at aecservicetech.com, that's going to be the main place where we sell this book. We're also going to be selling it on Amazon and also Google Play, Apple iBooks. So you can get it at all those places, and that'll be starting January 1st. And the reality is we're going to be taking some of the books down to the HVACR Symposium, and so we'll be there as well, and we'll be speaking about it there. So I look forward to seeing a lot of the hungry technicians that want to just soak up everything when we come down there. So I'm really excited about that.
Figuratively hungry, because we will be feeding them. So they won't hopefully be. Now, don't diss the food. The food is good. We got Chick-fil-A, the Lord's Chicken. We've got some great Latin fare. We have some barbecue. It's going to be the same smorgasbord. No, we're super excited to have you down. It's been great getting to know you. If for any of you who aren't subscribed to Craig's channel, AC Service Tech, I think the entire AC world is at this point. He's got like 40 zillion subscribers. But if you have not, then please go and do that. And then he'll make more fun of me when he gets his gold play button well before I do. It's going to happen. Do you know that to this date, the only silver play button that I have is the one that you made for me. They never sent me my silver play button. And
Are you kidding me?
Yeah, I think you called Mr. YouTube to make sure that I didn't get mine. I think that's what happened here. Anyway, go subscribe to AC Service Tech on YouTube. Follow Craig. He's getting more savvy on all of the social media platforms. You see more of him out there now, and going to events and all that. It's good to see you. I think are you going to be at AHR as well?
Yes.
AHR as well. Awesome. So so you get a chance to. Okay, great. Yeah. Oh, the HVAC Excellence. You're going to be speaking there as well. Yeah. So these are all things that I'm going to also be at. AHR, HVAC Excellence in Vegas. Those are all places that you can chase Craig down and tell him how much you love him. Appreciate you for all the stuff you do. And yeah, everybody go out and get the book on January 1st. It's going to be an amazing book. The book that you already put out on, just regular refrigerant cycle, all that stuff is Basic Service Practices. Again, remind me the name of that book as well. The name's not on top of my head.
That's fine. It's refrigerant charging is service procedures for air conditioning. And that's like checking the refrigerant charge, troubleshooting while measuring superheat and subcooling, and all the practices that you would do to prepare a system for refrigerant and service. Yeah. It's all refrigerant based.
Yeah. Great book. Super well illustrated. Really, really nice. I've bought a bunch of them, given them out to all my technicians. That's how good it is. So yeah, go out and get this book when it comes out. For anybody who's doing a lot of servicing on mini splits, or if you've kind of avoided it because you've been afraid of working on mini splits. I know there's a lot of contractors out there who are that way. This is a good way for you to kind of get more comfortable doing that. So Craig, thank you as always for coming on, and look forward to seeing you soon.
I appreciate everything you're doing, Brian. Thanks, man.
Thanks for watching our video. If you enjoyed it and got something out of it, if you wouldn't mind hitting the thumbs up button to like the video, subscribe to the channel, and click the notifications bell to be notified when new videos come out. HVAC School is far more than a YouTube channel. You can find out more by going to hvacrschool.com, which is our website and hub for all of our content, including tech tips, videos, podcasts, and so much more. You can also subscribe to the podcast on any podcast app of your choosing. You can also join our Facebook group if you want to weigh in on the conversation yourself. Thanks again for watching.